dear students. In the last chapter of atom and molecules, we did talk about atoms and molecules, and I thought every one of you must be having some idea about atom and molecules. Now, it is important for you to know that the whole chapter of atom and molecules, that is chapter number 3, has been laid on the basis of the foundations laid by John Dalton. He discovered that somehow atom is the most tiniest particle and atom is totally indivisible. Now, in this chapter, that is the chapter number 4, that is the structure of atom, we are going to move forward with some new particular kind of concept which we are not going to consider the Dalton atomic theory there, right? According to John Dalton, he regarded that atom is totally indivisible. But in this particular chapter, we are with the discovery of some new kind of like subatomic particles. The whole postulates laid by Dalton were somehow disqualified in a sense. So we are going to move forward now. So in the last chapter number 3, that is atom and molecules, I did disclose about the 3 subatomic particles, that is electron, proton and neutron. So now in this particular class we shall try to understand how the discovery of these particular subatomic particles started there, and it is important for you to know that. So it was in 1886 there. It was in 1886. So this is the experiment laid by the 1886. His name is E. Goldstein. E. Goldstein. Okay. So here, now if you look at this particular diagram of here, this is negative here, this is positive here. So now you can somehow understand that there are 2 kind of electrons here. One is over here and one is on that side here. Okay. So now this is the positive, which we used to call as anode, and this is the negative electron, that is what we used to call as cathode. So in between that, there are gases which are at very low pressure, and we can take the example of gases as hydrogen gas. Okay. So now, what E. Goldstein did in 1886 is that when he passed electric current at a very high kind of voltage, what he came to know is that over here, on this side here, the wall of the gas discharge to here, he placed some fluorescence material. Fluorescence material. Do you know what is the meaning of fluorescence? Fluorescence means, we know fluorescence color. For example, the kind of like greenish yellow, the color of the tennis ball, the greenish kind of yellow, which we used to call as fluorescence. Now, E. Goldstein kept some fluorescence material over here to see what kind of like conclusion he is going to get from this particular experiment here. So when he passed electric current at a very high kind of voltage, what he came to know is that on that side over here there is a reddish kind of color, right? His observation was that the moment he is going to pass electric current, he saw some reddish kind of, this fluorescence plate is being turned into reddish color here, right? Is that clear? So with this he came to know that okay, something is coming up from this side here. I don't know what is that particle here. Okay, but the second thing is he also concluded that since this is the positive side, the something which is coming from that side is positive by nature. That is positive by nature. Is that clear? Now, one more thing you need to understand is that here, when E. Goldstein was conducting his experiment in 1886, what he did was he placed, and this is the cathode here. This cathode is perforated. Perforated means it has some holes in that. For example, if this is a cathode here, there are some holes in that. Okay, there are some holes in that. Is that clear? So if there are not even a single hole in that, then we won't be seeing such kind of like conclusion over here. Is that clear? So E. Goldstein, that is the person here, E. Goldstein, in 1886, he did that experiment and he passed a very high voltage of electric current. What he came to know is that the moment he passed electric current, what he came to know is that on that side the fluorescence is changing into kind of like a reddish color here. With this he concluded that some kind of particle is coming from the positive side, which is entering this holes and striking over here, which is why they are turning into kind of like a yellowish color. Is that clear? So he named that kind of like positive kind of ray which is coming from the positive side, he named it as Colonel Straw. Colonel Straw, which when we convert that into English word, we are going to name this as Canal ray. Is that clear? Canal ray. So now there were a lot of discussion from the 1886, but it was in 1919 here. It was in 1919 with a scientist named Ernest Rutherford. His name is Ernest Rutherford. Ernest Rutherford. Right? What role he played here? The experiment was conducted by E. Goldstein, but it was Ernest Rutherford who said that positive particles which are traveling from this anode to cathode, he named this as proton. This is the subatomic particle which we knew, right? And this proton is normally positive by nature. They are normally positive by nature. Is that clear? Okay. Did you understand this part here? Now, secondly, J.J. Thomson, another scientist. There was another scientist, his name is J.J. Thomson. Who also did the same kind of like experiment here in a gas discharge tube. The whole set is totally same, but in this case, what he did was, he placed some fluorescence on that side here. Is that clear? Understand? So the moment when he passed electric current, what he came to visualize is that this one is turning into kind of like a greenish kind of color here in this gas discharge tube. So once again he considered that, okay, there are some particles which are coming from the cathode side. And from the cathode side, this particular kind of particle which are going to come from the cathode side, they are always negative by nature. Is that clear? So this particular kind of ray is what he termed as cathode ray, which he later said that this cathode ray is made up of negative particle, which he called as electron. And it was in 1906 he was awarded Nobel Prize for that, J.J. Thomson. So from this particular two kind of setup, what is important for us to know is that E. Goldstein was the person who conducted the experiment of gas discharge tube, and it was Rutherford in 1919 who named it as proton, and it was J.J. Thomson who discovered the electron here, and he was awarded Nobel Prize. Okay, so now we understood somehow like two kind of like subatomic particles, that is proton and electron. Now let us move for the next one. Okay. Okay. So now in the third one, what is important for us to know is that there are three important subatomic particles here. We understood about the two things here, that is proton and electron. Now, it was in 1932 here. His name is James Chadwick. James Chadwick. He did an experiment, okay. What he did, he kept some beryllium. You know, beryllium, right? Beryllium. He kept some beryllium atom over here. And to this, what he did was, he passed some alpha particle here. Alpha particle. Now you must be thinking, what is that alpha particle? Alpha particle is nothing. Alpha particle is helium here. Helium. With a mass of 4 and atomic number 2. When he passed the alpha particle, what he came to know is that if there is a positive kind of like sign over here, negative sign over here, he saw some mysterious material right? Mysterious material which are passing through that. Understand? And what was like, what shocked him was this particular material when it is passing from that position to that position. What he came to know is that this is neither attracting toward the positive side, and this is neither attracting toward the negative side, but instead it went straight away like this here. So with this, what he confirmed that the mysterious particles which are being kicked off when the bomb alpha particle is bombarded in a beryllium atom here, he saw some mysterious particles being shoot up here from this direction here. Okay, this mysterious particle doesn't carry any kind of charge, but it is having some amount of mass. Do you understand? So James Chadwick experiment was, he bombarded alpha particle on beryllium atom here. When he bombarded alpha particle on beryllium atom, what he came to notice is that there are some mysterious particles being shot up here. But these mysterious particles are neither attracting toward the positive side, and they are also they are moving toward the negative side, but instead they used to go in a straight way. What does that mean? They are neither positive, they are neither negative. So he named that as neutral, which is having some mass, but their charge is totally neutral here. Their charge is totally neutral. This is up here. So with this, we came to understand that in an atom there are three subatomic particles here. That is proton, electron, and neutron. Now in the previous chapter, according to John Dalton, he said that atom is totally indivisible. But now over here, we somehow came to know that there are like some more tinier particles than the atom itself. So you now must be thinking, okay, is the Dalton atomic theory totally legitimate now? Is it like, do we consider Dalton atomic theory? Do we consider that? You must be thinking that, right? So now on the basis of that, there are like many kind of scientists in the late 18th century, in the beginning of 19th century, who were struggling so hard that since we understood there are like three kind of things here. That is proton, there are like electron, and there are like neutron. Okay? So with the discovery of this kind of three subatomic particle, now people were asking, okay, since these three subatomic particles were present in an atom, how they are arranged? Where are they? Is proton revolving around the center, or is electron revolving around? They have so many different kind of questions, and people were thinking about all that. So with this, we are going to come across a different kind of like models or the theories proposed by the great scientists there. So I shall continue that in the next session there. Thank you very much, all of you. So in the previous session, we did discuss about the three subatomic particles. Now, in this session, we are going to talk about the Thomson model of atom, which was this model of atom was designed by J.J. Thomson. His name is J.J. Thomson, and he did that in 1904. And this particular kind of like model of atom came after the discovery of electron. But this model of atom, at the time of the model of atom, that is Thomson model of atom, people do not have much idea about the atomic nucleus. Okay, so this Thomson model of atom is also referred to as Plum-Perry model of atom. Plum-Perry model of atom. Okay. Now, why this particular model of atom came into our chemistry textbook is that there was a craze in late 18th century with the discovery of a new kind of things about the atom and the subatomic particles. Now, people are really crazy about how these kind of like subatomic particles are arranged within the atom. So they were trying to get some new information about the arrangement of the subatomic particles. So with this, the first foundation was somehow like took by Mr. J.J. Thomson in 1904. Okay, so he named this as plum pudding mortem. But please, I should remind everyone of you that plum in 19th century in English in England they used to refer plum for raisin. Raisin. Okay. Do you know what is the meaning of raisin? Raisin in our Tibetan language we used to say kundum, right? Kundum kampudi, right? So this particular kind of like a raisin, pudding model atom, right? Okay. According to J.J. Thomson, he meant that. But many of the people they used to understand plum as the normal kind of like plum fruit which we used to have in our daily life. This is not the case here. Okay. Now this is the pudding here. Pudding is something which we knew it with curd. We used to put raisin and everything. Okay. So now Thomson Mountbatten. In this, what is important for you to imagine is that just think about the fruit called watermelon. Okay. Let us consider this as watermelon. Okay. And all these are the red edible parts which we really used to eat. We used to like and eat. And this particular kind of like that thing over here, this is the black seeds. Okay, these are all of the black seeds. Now let me ask you one thing here. When we buy watermelon, okay, the one of the most difficult tasks for every one of us is that taking the seeds out, right? Because that particular seeds are present within the red edible parts, which is why we are having a difficult task taking it out. Otherwise, if we are going to eat the watermelons just like mango, then it could be a very beautiful thing for us, right? But since we have to take out the black seeds there, so similarly, Thomson, according to him, he said that if this is an atom, the electrons, that is the electron is the negatively charged here. I wrote negative here, negative. Understand? Negative here. The negative charged particles, they are embedded here. He used one particular kind of word, that is embedded. Embedded. Okay. So he gave two kind of postulates here. Postulate number one, he said the negative charged particles, they are embedded. That means they are present within the positive sphere. Just like the black seeds, they are embedded within the red edible parts. Is that clear? So this particular kind of model, symbolizes somehow, works in a very good kind of analogy with watermelon. Okay, so that was his first postulates. Okay, he said, okay, I will just write over here in a short kind of way. Okay, negative electron, right? Negative electron, they are embedded in okay. Did you understand this here? Negative electrons, they are embedded in positive spheres, and he doesn't even have much idea about the positive spheres. Okay? Okay, is that clear? Now, let us imagine, okay, we brought one watermelon, and now we are going to eat that. If I ask you one question here, out of this, there are two things in the watermelon. One is the black seeds and one of the red edible parts. Which one is more edible? So when you think about the black seeds and red edible parts, if the black seeds are more in number, then what is the purpose of buying the watermelon then? Right? We are not there to eat the black seeds, but instead we wanted to eat the red edible parts. So normally, he said, according to J.J. Thomson there, he said that it doesn't matter, right, whether these negative electrons are more in number or this red edible part is more in number. Is that clear? Because normally in watermelon, what do we see is that these red edible parts, these positive red edible parts, they are more in number, whereas the black seeds, they are less in number. We knew that. So according to J.J. Thomson, what he said was, it doesn't matter whether this particular kind of electron is more in number or the red edible part is more in number, but the total magnitude is same. Understand? For example, let me give you one small kind of analogy over here. Okay, there is a guy, he's pulling a rope here, playing a tug of war with three small girls. Okay. Okay. So now this guy, he is much more taller and much more fatter, much more stronger compared to, let's write 4 here. Okay. 4. He is playing a tug of war with these 4 girls here. Now, when they are trying to play this particular kind of like tug of war, these rope, they are not moving exactly at the center. Why? Because the total strength of this particular one person is equal to the total strength of these 4 girls over here. Is that clear? So, but what do we see here is that we see one boy and 4 girls. There is a difference in number. But what about the magnitude, right? If he is having an energy of like 50 joule, understand? If he is having a 50 joule, then the total energy of all 1, 2, 3, 4, these 4 girls should be 50 joule. That means the magnitude is same. Understand? Is that clear? This is in that case here. Now we are going to use this analogy over here. Let's imagine this positive sphere, that is the positive sphere, they are more in number. And this negative electron, they are less in number here. This positive sphere, they are more in number here. All over the places here. Understand? All over the places here. They are more in number. But what he concluded is that it doesn't matter which one is more in number, but the total magnitude of the negative electron and the positive sphere is same, which is why atom is neutral. So the second point was very important regarding the neutrality of the atom here. Neutrality of atom. Okay, second point is very important because let us imagine, okay, if atom is not neutral, if atom is either positively charged or either negatively charged, then I think that the whole concept of atom is going to change, and I just doubt, okay, whether any living organism will survive in this world. Is that clear? So the second postulate was, he said atom is neutral. Why he said atom is neutral? He said it doesn't matter which one is more in number, because the total magnitude of the negative electron and the positive is same here. Okay. Magnitude is same in electron and positive spin. Okay, so this is about the what do you call the model of the J.J. Thomson model of atom. But this was the first step towards the kind of like the design or the structure about an atom. So this was the first step, and as we see that this particular kind of model of atom is something which we don't consider nowadays, right? Because J.J. Thomson model of atom failed to give an explanation or to reason out any kind of connection between the negative and the proton there. They failed to show off any kind of relationship between these two. That is why the later kind of model of atom speaks about the relationship between these two. Understand? Okay, so we shall discuss in the next session then. Thank you. Okay, so hi once again everyone. So with the drawback of J.J. Thomson model of atom, it was followed by Ernest Rutherford. He is also referred to as the father of nuclear physics, and in this particular model of atom, he was trying to explain the arrangement of electron and nucleus, which he had discovered somehow. Okay, so let us proceed with the understanding of Rutherford model of atom. But before we try to understand the Rutherford model of atom, let us first try to see what kind of like things we had used and what are the reasons behind it. Let's say why gold foil here. There are so many kind of like let us take an example of this book over here. Okay, why gold foil? Rutherford has used gold foil as a source, as the atom to which he is going to strike the rays there. Okay, so he took the gold foil as an example because there are two reasons for that. Number one is gold foil is very malleable here. Malleable in the sense that they can be written down into a different kind of thin sheets there. Okay, so because of the malleable nature of the gold, we are using gold in the form of gold chain, gold biscuits, and earrings and everything, right? And the second important reason behind why Rutherford was choosing gold foil is gold foil was extremely thin. Understand? So the thin nature of the gold foil, they are very helpful, or they are very it gives you a more clarity in detecting the every single kind of changes which you are going to observe in this particular experiment here. For example, here I have this book here. If I'm going to drop a chalk on this particular book here, it is going to make some sound, right? But if I try to drop this particular kind of this is a page here on this particular, this is going to make more sound here. So keeping that kind of like this a small kind of analogy here, the thicker substance, they are like giving you a more lesser clarity regarding the detection of the object, whereas the thinner one gives you more clarity or the more idea about what kind of changes going on. So the second one, why we are choosing gold foil, because they are extremely thin by nature. Okay, yeah. So this is the gold foil here, and in this particular diagram here, this is the gold foil here. These round things, these are the gold foils. Now I hope you all have understood why Rutherford has chosen gold foil. Now let us go for the next one. Why alpha particle here? Normally there are different kind of particles here. For example, let's say there are alpha, beta, gamma, and all of this. If you look at alpha particle, this is like the formula is 4He2. If you look at the beta particle, it is 2H1 here. Now, if you look at this particular kind of particle here, this is 2 and this is 4 here, and these are the mass. Okay. Now, which one is having more mass, 2 or 4? 4 is having more mass, right? 2 and 4, 4 is having more mass, right? So, one of the reasons behind why Rutherford is choosing alpha particle is because that alpha particle is moving at a very high speed from here to there. It is going to strike at a very high speed that we won't be able to measure it. Is that clear? Even in this case here, this alpha particle is moving from here to there at a very high speed. Is that clear? Okay? Very high speed. And another reason is this alpha particle, they are positively charged by nature. They are positively charged by nature. So, but the basic reason behind why Rutherford was choosing alpha particle is because alpha particle is very heavy. Let's suppose imagine if you are driving a motorbike, let's say Enfield. Normally Enfield is regarded as a very heavy bike. If you are traveling at a speed of like 150 km/h, that means this particular bike, since it's being very heavy, there is a very less chance that this particular bike is, because of the wind speed and all of this, we won't be able to see that this bike will move in a straight direction. I'm sorry, we will be able to see that this bike will be able to move in a straight kind of direction here. But if you are traveling on a bike, let's say Yamaha here, a much lighter bike, if they started to travel at 150 km/h, and I'm sure this particular bike is going to fall down at some point. Why? Because of the wind resistance, this bike being very light, it will fall down at some point here. So, since in the same case here, this particular ray has to travel at a very high speed, in order to strike this particular gold foil at his own target, he chose alpha particle. Why? Because alpha particle is very heavy. Is that clear? Okay, so now with this we are going to proceed here. I have written two different kind of diagrams here. You can represent that both are same somehow, okay? But they have a different kind of representation here. So now what Rutherford did was he kept some gold foil. In this you can see the gold foil atoms here. Okay, in this you can see one gold foil here. Now to this what he did, he passed so many kind of alpha particles here. Okay, so many kind of alpha particles. Now I'm going to consider that for the 100% here. 100%. Out of 100%, what he noticed was like almost like 70%. Okay, let's say 70% are traveling in a straight kind of direction here. Straight kind of direction here. Is that clear? 70% is traveling in a straight kind of direction here. That means 70% is traveling in a straight. That means they are not getting deflected. Number one. I'm sorry, I haven't shown it in this one over here. Because this is one over here. But in this case, I can show you somehow. 1, 2, 3, 4, and here on this side. 5, 6. Okay. So from 100% of the rays, 70% of the rays, they are traveling in a straight line. Okay? They are not getting deflected. Not getting deflected. They are moving in straight. Moving in straight direction here. Okay? But out of this, 29%, let's say 29%, okay? 29% are deflecting at different angles here. You see that one. 1, 2, and 3, and 4. 29% they are deflecting at different angles. Understand? 29% are deflecting at different angles. At different angles. Okay. Now this was the observation made by Rutherford. Okay. Out of this, 1% here, this particular ray is going to strike this. Is going to strike this and is going to fall back at 180 degrees here. Understand? So what he concluded that third one, 1% of the ray is deflecting at 180 degrees. Okay? Let's conclude like that. Understand? So this was the three observations made by Ernest Rutherford regarding his atom here. Now, we will try to understand what are the conclusions made by him, right? Okay, so when he made these three observations, he made some conclusion which is also referred to as nuclear model of conclusion. Model of conclusion here. Okay, so conclusion number 1. So when 70% of the ray is moving in a straight line without deflecting, what he concluded is that naturally this is an atom here, Wolford atom, has many space. Has many empty space. Many empty space. Okay? Understand? When 29% is deflecting at different angles here, this 29% deflecting at different angles, what he concluded is that something, let's say something that is very heavy. Understand? Something that is very heavy is at the center. Is at the center. Okay? Because we knew that an alpha particle is very heavy. If something which is present at the center is not heavy, then they are not going to get deflected here. Understand? Since alpha particle is deflecting at different angles here, the something which is present at the center is very heavy there. Understand? That is the second conclusion. Now the third conclusion here. What we knew is that alpha particle is generally positive by nature. When this particular kind of positive ray comes over here and collides at the center, what do we see is that they are not attracting here, but instead they are repelling. Understand? For example, if this particular positive ray strikes over here, it repels in that direction here. If it strikes over here, it repels in that direction here. But if it strikes at the same point here, that point here, it repels at 180 degree here. So what do we come to know from this point is that the something which is present at the center, they are positive by nature. Why positive? Because the positive ray and this positive, they repel each other. Is that clear? Because that positive alpha particle is coming with a polarity of positive charge, and the something which is present at the center, they are also positive by nature, and this positive and positive repel each other. We knew that, like charge repel, right? So something which is heavy and which is at the center, they are positive by nature. Positive by nature. Positive by nature. Is that clear? Which they somehow termed it as nucleus. Is that clear? Okay? So now these are the conclusion made by nuclear model atom. On top of that, he also made one conclusion that electron revolves around the nucleus here. Electron revolves around the nucleus. So on the basis of that, the one more topic, that is the drawback, okay? Okay. So this number third, that is the fourth one here. Electron revolves around nucleus. Now, to this particular fourth postulate, the drawback or drawback. Do you know drawback means the weakness? Drawback of Rutherford model atom starts here. Okay. Now let us consider this is the positive and this is the electron here. Okay. This electron revolves around the. He says that electron revolves around the nucleus in a particular kind of orbit there. Okay. So let us imagine. Okay, if there is a track here. And there is a person who is going to run. Okay. So he is running a race of 1,500 meter race. That means he has to cover 7.5 rounds. Understand? So the moment in the first round, he is going to run at a greater pace, and gradually, what will happen at fifth round and sixth round, his pace will decrease. Why? The energy present within his body will also decrease. Is that clear? Why? Because this guy, when he runs, he keeps on exhausting his own energy. So in the similar way, electron is negative by nature. So when electron is revolving around the nucleus here, what is happening? Electron is also losing energy. Understand? Also losing energy. Now this was the kind of like accusation made by the other scientists about the Rutherford model atom. Okay, so now there are some energy losing. If the energy loses, what will happen? This electron will gradually negative and positive, they attract each other. So if the energy loses, this negative will gradually come closer to nucleus, and at some point they are going to collide, or they are going to join with the nucleus over here. So if this happens, then the whole structure or the whole concept of atom is not going to exist. Is that clear? So that was the drawback of Rutherford model atom. According to him, he said that electron revolves around the nucleus, but Rutherford failed to mention about the losing of the energy, which is why the other scientists says that if any kind of subatomic particles revolves around the nucleus, there will be energy losing out. If this energy loses out, electron is negative by nature and this is positive, they try to attract each other, so somehow it will gradually collide with each other, which is not at all acceptable. So in the next kind of like model, we will discuss about the energy, electron revolving around the nucleus and the energy. Okay, so thank you very much. Have a nice day, all of you.